1.5, and so it talks about families of functions, and a family of functions is basically a group of functions that are similar. So for example, all of the quadratic functions are a family of functions, right? All of the absolute value functions are a family of functions. And the parent function is basically the parent function is actually the most basic form of, what do you call it? Of that function, right? So for example, if we take the family of the quadratic functions, y equals x squared is the basic form. We call that the parent function, right? And then all these other quadratic equations are, they are derived from that one parent function, x squared. All right. So let's go through some of the most basic or most common parent functions. One is a constant function, right? This is the first thing we're going to talk about. So for example, if you have f of x is equal to 3.5, right? That's all it is. It's y equals 3.5. It's a horizontal line. That's the whole function, is a horizontal line that crosses y equals 3.5, okay? And that's a constant function. Next, we have the identity function, f of x equals x, okay? Or y equals x. So if you do have y equals x, when x is 2, what's y? When x is -5, what's y? Hence the term identity function, right? So x and y are the same. So that's the identity function. The graphs of those are are the graphs of the linear functions. And if you have something like this, 3x minus 7, again, that's just a derivation of f of x equals x. All right? Next up, we're going to talk about the quadratic functions. F of x equals x squared is the parent function of the quadratic functions. Their graphs look like a parabola. What I want you to remember about this is this an even or an odd function right now? F of x equals x squared, huh? It is an even function, right? And if it's x squared, right, it's an even exponent. You see how so that's an even function, and as far as the end behavior, both ends either go up or down, right? But basically both ends will face up together or they'll face down together, all right? Now, to graph one of these, my preferred way, a quick way, of course, like you can have your own way, but one quick way is because it's x squared, y's increase as you square your x values. So for example, the vertex here is 0, 0. If I go over 1 unit, I go up 1 squared unit. But if I go over from the vertex 2 units, I go up 2 squared or 4 units, and so on. All right? From the vertex. And then it's symmetric the other way. Now, next up is a cubic function. A cubic function is an odd function, right? And if you see at the infinities, the end behavior, one end will face up, one end will go down.
Could you tell if it's an even or odd function just by the end behavior?
No, like an odd function. So these also have to be centered at the origin or on the y-axis, right? On the y-axis for this and that one. So if I shift this one, it'll no longer be an even function. F of x equals x squared is an even function. Not all quadratic functions are even functions. However, they do exhibit the behavior that they have the same end behavior. Okay? Yeah, more on that in the next chapter as well.
Okay.
So the way I graph these, a quick way, right, is since it's a cubic function, from this center, if I go over 1, I go up 1 cubed. And if I go over 2, I go up how much? 8. 2 cubed, 8. All right? All right. And same symmetrically that way. Over 1, down 1 cubed. Over 2, down 2 cubed. All right. Next up. Square root and reciprocal functions. All right. So here is a square root function. F of x is equal to root x. The thing about this is, if you just look at the root x and you look at the domain, you know that anything inside should be greater than or equal to 0. The stuff inside is called the radicand. And we know that it has to be greater than or equal to 0. So, can this x be negative 2? No. Can it be 0? Yes. So only positive 0 or positive numbers can go inside that root as it stands now. And you see how that matches with the graph, because the graph only exists over the x values that are positive. It doesn't exist over the x values that are negative. So you see how the domain based on the function matches how the graph looks and the domain on the graph, right? So, 1 second. There's something else I wanted to tell you about that. Okay. Right. So it only exists over the values which make, okay, so graph exists only on values which make the radicand greater than or equal to 0. Okay. Next up, reciprocal function. These are really like the VIPs of the functions now, right? Reciprocal function is f of x is equal to 1 over x. Get it? It's the reciprocal of x. Okay. Can x be any positive value in that equation? Yeah? Can x be any negative value? Yeah. Can x be 0? No. So the only thing is x cannot be 0. So here, x cannot be 0. So anything, on that vertical line is off limits. That means there is a vertical asymptote at x equals 0. All right? Now, let's take f of x equals 1 over x one more time. If x is 1, what's y? 1. If x is a half, what's y? 2. If x is a fifth, what's y? 5. They're getting bigger, right? Okay. If x is 10, what's y?
1 over 10.
Okay. If x is 1,000, what's y? 1 over 1,000. Okay, now they're getting smaller, right? Okay, so if x is 1,000,000, what's y? 1 over 1 million, right? So give me a number to put in here to make it 0. 1 over what to get 0? 1 over 1? Not 0.
You can't.
You can't.
Yes.
There is no value of x that will make this 0. Okay, can y be negative though? What if like x is negative 5?
Of course.
Yeah, y can be negative. It can be positive. It could be as high as you want. It could be as low as you, but it can never be 0. All right? So there is no x value that would make the y 0. Therefore, y can also not equal 0. So that's out as well, meaning there is also a horizontal asymptote. HA is horizontal asymptote. at y equals 0. Yeah, like these are two imaginary perpendicular lines. All right. Last one, absolute value. Absolute value, right? Y equals absolute value of x. Fabulous. So let's see for what values this exists. Can x be 0? Is x allowed to be 0? Yeah. Is x allowed to be positive?
Yeah.
What about negative?
Yeah.
So the graph does exist over the entire, number system, right? Negatives, positives, and 0. Now, is y able to equal 0? Can you come up with an x value to make y 0? X equals 0, y is 0. Okay? If you put a positive value in here, like positive 5, what's y? 5. If you put negative 5 in there, what's y? 5. Is there any way to make it negative? No. So that's obvious from the equation, and it's also obvious from the graph, right? Because x can be any number, y can only be positive, and you see it doesn't even exist anywhere that y is negative. Now, let's take a closer look at this function. Okay? Do you see how it looks like it's made up of two different segments or rays? Don't piecewise functions also look like that? Yeah? So if I were to ask you to write a piecewise function for this, would you be able to write a piecewise function for it? Where is the split? Right here, isn't it? Right? So what would be a proper function for the stuff on the left? I'm sorry, on the right. F of x equals x, right? Slope is 1, y-intercept is 0. What about here? F of x equals negative x. Slope is negative 1. So I can easily write a function that's negative x on one side, positive x on the other side, right? X is less than 0, x is greater than or equal to 0. Look at that. You have two different interpretations of the same function. Okay? So if I were walking down the street and I saw a large billboard, a white billboard, and on the billboard it just said this, I would look at that and I would go, oh, that's absolute value of x right there. Negative x, positive x. Okay? Right? They're the same. Okay, so these were the parent functions, the default form of each of the families. Transformations affect the appearance of a parent graph. Transformations, any type of change. The first type of transformation we're going to do is a translation. A translation shifts the graph up or down or right and left. I left that out. All right, so let's see how it looks. This is familiar to you from Algebra 2, right? Mostly, somewhat, a little. Okay. So, look at this function. This is y equals x squared, right? Well, if I wanted to move it up, it would look like y equals x squared plus 5. Okay? Moved up. And if I wanted to move it down, it would look like y equals x squared minus 4. So I add a plus k to move it up, a minus k to move it down. Now, if I wanted to move it sideways, I would have to do a little operation on the x, not the y. So, if this is f of x equals x squared, this is g of x equal to x. What do you think? What would be a convenient or an appropriate function for this? What do you guys think?
X minus 2.
Look at that, right on the money. X minus 2 squared would be a completely appropriate function.
Why?
Let's see why. Because in order to figure out the transformation, you take, okay, this tells you something has happened to the x. The x has shifted. You take that and you set it equal to 0. And when you solve, you get x equals positive 2. That means it moved in the positive direction
It's like the,
2 units. It's inverted or reverse.
It's H.
It's huh?
Because it's H.
Because it's h. So tell me an appropriate function for this one. G
Minus two.
plus 2.
x plus 2 squared. Yay. Okay, so let's do it then. Let's graph a couple. X cubed minus 3. So we're going to use f of x equals x cubed to graph this. For this one only, I'm first going to graph the parent function x cubed. So x cubed, you should now know after this lesson that x cubed, it's how you should know how it looks. So basically it stretches up on one side, down on the other side. It's centered at 0. And then if I go over 1, I go up 1 cubed. If I go over 2, I go up 2 cubed, 8. And symmetrically on the other side, over 1, down 1, over 2, down 8. And it looks a little like this. This is f of x equals x cubed. Now, what happened to this function g of x? What does that minus 3 do to the function?
Shift it to
To the right.
the left.
Vertical translation.
You thought right. Say that again louder.
It's a vertical translation.
It's a vertical translation where? Down. Why? Because it's not grouped with the x, right? It's outside. This affects the y, not the
If
x.
it was x minus 3
Cubed, then it would have shifted. Okay, so that means each of these points are going to move down 3 units. So 1, 2, 3, 1, 2, 3, 1, 2, 3, and so on. Okay? Like this. Cool? Now, okay. Now, I'm not going to have you do it this way all the time. So for that one, okay, the point of Precalc Honors is to just be quick on your feet with these. So we're just going to go right into it like pros, right? Okay, let's do it. What transformations do you see here on B, h of x?
To the right, 4 and up.
Horizontal and vertical to the
Right,
right, 4 and up 2.
Hi, buddy.
So it's still a cubic function, but now the center has shifted right 4 up 2, right there, 4 comma 2. Now, from there, all right, I'm going to go over 1, up 1, over 2, up 8. Okay? So this point is at 5 comma 3, 6 comma 10. Same way, over 1, down 1. Over 2, down 8 to negative 4. Okay? Oh, I'm sorry, negative 6. Thank you. So here we go. All right. And do you see how I effortlessly labeled 3 of the points over there? 3 coordinate points? I'm going to ask you to do that on your assessments, tests, quizzes, and so on, right? You see how I didn't waste too much energy on that, right? Okay. So there we go. We just did that like a pro.
You don't need to graph the parent function.
I don't want you to have to graph the parent function and then go there. I want you to go to the end game from the get-go. All right? Okay. Now, a reflection. Okay, so next we're going to talk about reflections. You can have a reflection in the x-axis, okay, in layman's terms, flipped over vertically, but we're not going to use that because that is not professional language. We're going to use what we call language of the discipline.
Wouldn't it not be a function then?
No, oh, no. So, but it's not both. Like, originally it was the blue function, then it shifts and it becomes, right. So the way in which you know that is there is a negative in front of the function. So if f of x stands for the y, when you put a negative in front of it, it basically switches the sign of all of the y values. So whatever is positive becomes negative and vice versa. Okay? So that's a reflection. So we say this has been reflected in the x-axis or reflected about the x-axis, around the x-axis, not flipped over, not a vertical whatever, flipping or whatever, right? I will not give credit for that. Language of the discipline, technical language here. Then we can have a reflection in the y-axis. What happened here is we make the x's negative. Okay, so let's take a look at that. Y equals root x. Okay, that's the original function, blue. What are all the possible x values that can go into this blue y equals root x? Can 0 go in there?
Yeah.
How about all the positive numbers?
Yeah.
How about all the negative numbers?
No.
No. However, if I switch it and if I say g of x is equal to the square root of negative x. Now, can 0 go in here?
Yeah.
Can all the positive numbers go in here?
No, it's
No. But can all the negative numbers? Yes.
Yes,
So
ma'am.
do you see how it now switches and now it only exists on the negative x values and not on the positive ones? You see the power of math?
Yeah.
Okay. Okay, so that's a reflection in the y-axis. All right, so let's do that then. We're going to use the graph of root x. So again, for this first one, I want to graph the parent function f of x. All right, the square root, you should know what a square root graph looks like, right? You should be able to recognize it like a mile away. It has an endpoint here at 0, 0. Now, if I go over 1, how much do I go up this time? How much?
Go up 1
Well, yeah, but if I go over 1 to the right, how much do I go up? Not 1 squared, not 1 cubed. Square root of 1,
So 1.
so 1. Now, we're going to work smart, not hard. So I'm not going to go over 2 because then I would have to go up the square root of 2, and that's just silly. So you do 4, and I go up 2. You see that? And then I can go over 9, and I go up 3. You see? It's like a whole different ball game. All right. That's f of x. When you have more than one function graphed on the same set of axes, label your functions. This is the professional, elegant way of doing it. Okay? All right. All right. Now, negative root x plus 4. What transformations do you see?
Vertical.
Vertical what? Because there's all sorts of vertical things, huh?
Oh.
Vertical shift. So, vertical
What did it
translation or shift, I'll take both. Vertical translation up 4 units. Okay? On the test, I will ask you to write down the transformations, okay? What else is there? A reflection where? Reflection around, not the y, the x-axis. Because if the negative is outside, I'm going to say what I said not to say, it's flipped downwards. It's a reflection in the x-axis. Okay? All right. So now, the endpoint then starts at 4. So, if I go over 1, I should have gone up 1, but now where do I go? Down 1. It's just like when you were graphing the sine functions, right? Instead of going up, if it was negative, you would go down. So if I go over 4, I go down 2. When I go over 9, I go down 3. And that's how it looks. Yay. Okay, next. This one goes to the left 1, up 2. And there is a vertical translation. I'm sorry. There is a reflection around the x-axis. So, left 1, up 2. Okay? Now, if I go over 1, I go down 1. If I go over 4, I go down 2. So that's at 3, 0. Because it moved left 1.
And you go down because it's
X plus 1, it's x plus h. So I go left 1, huh? And if I go over 9, that'll put me at 8. I go down 3. Okay? They look like inverted commas. Okay. Okay. So, vertical and horizontal dilations. Okay. All right. So suppose this blue parabola, x squared. Suppose it was like a rubber parabola, right? And I attached like a little, what are those called? Oh my gosh, what are those like round cylindrical things called? Oh my gosh. No. All right, no. All right, whatever. Suppose I attach like a handle to them, right? Although that's not what I'm.
Like a rubber band.
No. Never mind. I'll tell you right now. It'll pop. I'm having like a senior moment here. So suppose I attach a handle here, right?
Okay.
And if I pull up, what happens? The whole thing gets stretched upwards and it narrows, right? If I were to pull up, it'll become this, right? The green one. So this is a vertical dilation. When you pull up, it's expanded vertically. And then when I hold and I press down, what will happen? It'll like bulge at the bottom and it'll look like the red, right? That we say is compressed vertically. So both of these together are called, umbrella, it's a vertical dilation, and it's either expanded vertically or compressed vertically, right? Expanded, compressed. Now,
It's like it's all falling. There's like hand massagers. And you put it on to like expand.
it's exactly like that. It's exactly like that. Okay.
Oh,
Yeah. I actually have one of those. I should bring it. Okay. A horizontal dilation is when you grab it at the sides and you either squish it or you expand it, right? So that's called compressed or expanded horizontally. Okay? Now, for a vertical expansion, a has to be greater than 1. So for example, if this is y equals x squared, this one will be y equals 3x squared. You see, this number is greater than 1. That's a. Absolute value of a has to be greater than 1. Here, it's more like y equals half x squared. It's less than, it's a fraction between 0 and 1. Okay? All right.
So this one has to be less than.
Well, between 0 and 1, yeah. So not less than, like it can't be negative 3.
Okay.
The absolute value is between 0 and 1.
So A is between.
Yeah. The absolute value of a is between 0 and 1. Okay, so let's graph a couple. Okay, look at a here. What shape is that? I mean, what? It's an absolute value, right? Yeah. Okay, so you see how there is a vertical reflection?
Yeah.
Not a, sorry. A reflection around
So x-axis.
x-axis. And there is a vertical dilation there, right? Because, so is it expanded or compressed for that one? Expanded. Good. It's a vertical expansion. So now, all right. So now, the parent function is negative 4 absolute value of x. So I start here at 0, 0. And if I go over 1, I'm going to go down 4 and down 4. So that's how that looks. Okay?
Can you explain why it's a vertical expansion?
Because this a is greater than 1 in front of it. It's a 4.
Oh, I was thinking that as negative.
Right. But you always take the absolute value. That's why I said absolute value.
Oh, okay.
Yeah. So here, this one is a vertical, not expansion, but a compression. Okay. So here we go. That's a parabola centered at, the vertex is at 0, 0. Now, for a normal parabola, if I go over 1, I should have gone up 1.
You multiply that.
But now it's a factor of 1/4. So instead of going up 1, I'm going to multiply by a 4th and go up how much? 1/4.
I think I remember this one.
If I go over 2, I should have gone up 4. But I go up 1/4 of that. So how much? 1. And it looks like a much wider parabola. Okay? All right, next. Let's do this one. Okay, so f of x, all right, so piecewise function. This time we're not going to draw the partitions. Not anymore. We're past that. All right. First function here, right? X and y equals negative x plus 3. What x value should I put in there? What do you all think? Where's the endpoint there?
0.
0. 0, right? Because the endpoint is at 0, I put 0, so I get 3. So when x is 0, y is 3, and it's an open circle. Okay, now I want you to graph these by seeing the bigger picture. What shape is this, negative x plus 3? It's a line basically with a slope of negative 1, right? So you can just go up over 1 to the left, and that will be a negative slope, right? So here, 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 there. If you can't see it, put in another point from that region. Okay, next one. Y equals 2x. Okay, so what's one number I should plug in? 0. And I get 0. What's another number I should plug in? 3, because it's got 2 endpoints. So at 3, it's 6. So 0, 0, closed. 3, 6. This way. Lastly, x root x plus 1. What's the first number I should plug in? 3. And I get, oh look, 3 plus 1, 4, which is 2. So at x equals 3, it's 2. Okay, now, what shape is this? It's a square root graph, right? What's the next number I should put in? What's the next number I should put in so I get a perfect square underneath? I'm not going to put in a 4. 8 is good. It has to be on that side. 8 is good. Okay, to make it 9, so it's 3. All right? There.
So
Okay.
in that case, you would just take a number that like fit. That
Huh?
Like when you picked the 8, like you just did that because you knew that it would like work. Does that make sense?
Yes. Okay, so hang on. Let me stop this. I'm going to stop here, but you should start on your homework, right?